There are a few things to know before attempting to convert a base 10 decimal number into a binary floating point representation. In this video, we will cover how to dissect a number and how to normalize it. Don't worry, you're probably already familiar with the term normalize because it's also known as scientific notation. First, we must understand how numbers in general can be broken down. For base 10, this is how it looks when a number breaks down. Let's say 975, which is a whole number. Remember, 975 is the same as 975 times 10 to the 0 power. And remember that any number to the 0 power is 1. So 975 times 10 to the 0 power is actually 975 times 1, which is still 975. Now let's take a look at the positions of the digits in this whole number. We have 3 digits in this number, and if we number the positions starting right to left and starting with 0, we have 0, 1, and 2. We will use these position numbers later as exponents for the number 10 since we're breaking down a base 10 number. Let's look at how we would break it down. We have 9 times 2 to the second power. Notice how the 2 is the same as the position number. Then we have plus 7 times 10 to the first power, and the 1 is also the position number of the 7. And then 5 times 10 to the 0 power, which is the position number above the 5. That's the same as 9 times 100, plus 7 times 10, plus 5 times 1, which is the same as 900 plus 70 plus 5. So that's how a number is built up or broken down, however you want to look at it. Let's do another example. If we had 9,752, we have 4 digits, and we number their positions starting from the right at 0, and you can see we have 0, 1, 2, and 3 to represent the 4 digits. Remember, we'll use those position numbers as exponent numbers for 10. Here you can see we have 9 times 10 to the third power, which is the position number for number 9, plus 7 times 10 to the second, plus 5 times 10 to the first, plus 2 times 10 to the 0 is the same as 9 times 1,000, plus 7 times 100, plus 5 times 10, plus 2 times 1, which is the same as 9,000 plus 700 plus 50 plus 2. That's all equals 9,752. Now what I'd like you to notice is how the exponent gets smaller by an increment of 1 as we move from the left to the right. Or we could say that the exponent gets larger by an increment of 1 as we move from the right to the left. Remember that the rightmost number of a whole number should always have the position number of 0. Now that we understand how that works, let's take a look at how we would break down a number if it's not a whole number. Let's say it's a fraction. Let's say we have 0.75, and we are still working with a base 10 number. Since we have a decimal point, we will be decreasing the exponent as we move from the left to the right. If we look at 0.75 in our little position chart, we can see here that we have our decimal, and then after the decimal, or to the right of the decimal, we start immediately with a -1, then the next position is -2. So if we broke it down, it would look like this. 7 times 10 to the -1, notice that the -1 power is the same as the position number we have in our chart, plus 5 times 10 to the -2, which is the same as 0.7 plus 0.05, which is equal to 0.75. Just remember, if we're going to assign a position number, the digit just to the left of the decimal always starts with 0, and we increment by 1 as we go to the left. If you're at the decimal, any numbers to the right of the decimal, we always start with -1 and decrement by 1. If we had 975.75, the number broken down would look like this. Our first position number there for the 9 would be a 2, and then 7 would have 1, and 5 would have 0. Then we have our decimal, and then the 0.75, you can see it looks the same as the last one we did, which is -1 and -2. So when we write out the entire formula or equation, we have 9 times 10 to the second, because 2 is the position of the 9, plus 7 times 10 to the first power, plus 5 times 10 to the 0 power, plus 7 times 10 to the negative 1 power, plus 5 times 10 to the negative 2 power. So when we think about it visually, the position of the numbers are represented as you see in this number line. We start with infinity all the way to the left, and then as we decrement by 1, because we're going from left to right, we end up with 43210, and then our decimal, and then we continue decrementing negative 1, negative 2, negative 3, all the way down to negative infinity. So just below those position numbers, you can see where we've positioned our 975.75. I hope that helps you understand how those position numbers work. The second thing we need to understand is how to normalize a number. Sometimes this is called scientific notation. Now, normalizing a number or writing a number in scientific notation just means that there is only one non-zero digit to the left of the decimal point followed by the multiplication of 10 to some power. Well, let's say we have 975 again. We're still working with base 10 numbers here, and we want to normalize it. To do this, we would move the decimal from its current location, which is to the right of 5, because remember this number could be written as 975.0. Then we move the decimal 2 places to the left, and we arrive at 9.75. Now, since we moved the decimal 2 places to the left, we must use 2 as our exponent for the multiplication of 10 to some power. So our normalized number or scientific notation for 975 is 9.75 times 10 to the second power. If you put that into your calculator and multiply it, you'll see that 9.75 times 100 equals 975. Now, what if we had a number that had numbers after the decimal? Well, that's no problem. To normalize the number, we simply move the decimal point from its current location to the left again until there is only one non-zero digit to the left of the decimal point. In this case, we would move it 2 places to the left, and 975.75 would become 9.7575 times 10 to the second. The number of times the decimal moves to the left becomes the exponent. Now you may ask yourself, well, what if it is a small number, less than 1, like 0.0025? We would normalize it in a similar way, but since we're moving the decimal from the left to the right, we have to decrement the exponent we will use. So we will move our decimal place to the right 3 times. That makes the first non-zero digit appear to the left of the decimal point, giving us 2.5. Now, since we moved the decimal point, we have to remember to multiply by 10 to some power. Since we moved the decimal point to the right 3 times, that means the power is a negative 3, which means that 0.0025 is written in a normalized format as 2.5 times 10 to the negative 3. I hope that helps you understand how to break down a number and understand its positions, as well as how to normalize a number or write it in scientific notation. The next video in this series will help you convert the base 10 numbers to binary floating point representation. I hope you've enjoyed this video, and I hope it's helped. In this video, we are going to convert base 10 numbers into a single precision floating point representation. Here are a few terms that we need to understand before we dive in. The first term is sign. The sign will determine if a number is positive or negative. As with a signed integer, 0 indicates a positive number and 1 will indicate a negative number. You will see this in formulas represented as an S. The next term is exponent. This exponent will store a number that will allow us to determine the exponent of the normalized number, just like the exponent in the multiplication of 10 to some power we did in the previous video. The only difference is that now we will be using 2 instead of 10 for our base, since we'll be working with binary numbers. You will see the exponent in formulas represented as an E. The next term is fraction. This will represent the number to the right of the decimal within the number we are working with. Sometimes you will see this in formulas represented as an F or as the word fraction. Another term is mantissa. It's just a representation of 1 plus the fraction. It should make sense by the end of this video. The next term to be familiar with is bias. For single precision, the bias is always 127. There is a format to be familiar with as well. The format of a 32-bit single precision floating point representation is broken down like this. You can see position 31 is the sign, positions 30 through 23 is the exponent, and positions 22 through 0 is the fraction. This format shows the three variables we'll be working with. The rest of this video will discuss how we will arrive at the value for each of these variables. There is a helpful formula we also need to use. A -1 to the sine power times 1 plus f times 2 to the e, which is our exponent. First, we must convert our base 10 number into binary number. Let's use the same number we were using in the last video, 975.75. First, we will convert the whole number to the left of the decimal. The way I learned this was to take the number, divide it by 2, and then you will get a number and you may have a remainder. Now those remainders are important because they will be a 0 or a 1, which become your binary representation of 975. Remember, when we convert a number to binary, the last number we calculate actually becomes the first number in the binary number when reading it from left to right. That's because this number is before the decimal point. Therefore, our binary number for the base 10 number of 975 is 11001111, and that is a base 2 number. Now let's convert the fraction to the right of the decimal into a binary number, which will be 0.75. The way I was taught follows this algorithm. We multiply the fraction by 2. If the answer is greater than 1, then we write 1 as the binary number. And in the next iteration, we only use the decimal portion of the last number we calculated. So we basically ignore the 1 or subtract the 1 before we do the next multiplication. If the answer is less than 1, meaning that there is a 0 to the left of the decimal point, then we write a 0 in the binary number, and we just use the answer in the next iteration and multiply it by 2. We do this until we get a 0 for the decimal, or when we have used all 23 bits of the fraction, because remember from our format, the fraction consists of 23 bits. Whichever comes first, we'll stop. Now here with 0.75, we can see that by the time we get to the third iteration, then we've already reached our 0. Our first number is binary. This is our leftmost position right after the decimal point. We have a 1, and then we have another 1, and then everything else after that will be zeros all the way up to that 23rd position, because we can't leave it blank. It's got to be a 0 or a 1, so we'll just populate them with zeros. Now keep in mind, when converting from fraction to binary, we place the 1s and the 0 from the left to the right in the order which we converted them. Just remember, if the number being converted is to the right of the decimal, you keep the binary in the same order in which you converted it when reading from left to right. So now we know that the binary representation for 0.75 in base 10 is going to be 0.11 in base 2. So what we have to do next is we have to string the two binary representations together and separate them with a decimal. So we come up with 1111001111.11. So what do we do next? Well, remember in the last video we talked about normalizing the number? Well, we have to do exactly the same thing with our binary number now. Yes, you can normalize a number even if it's represented in a binary number. We will have to move the decimal to the left 9 times to arrive at our normalized number. And it will look like this: 1.111001111111. And if we add the multiplier to it, it becomes 1.1110011111. I think I've got enough ones in there, times 2 to the 9th power. Notice that the 9 is our exponent, and that is exactly the number of times we had to move our decimal to the left to arrive at our normalized number. Remember at the beginning of the video I mentioned the term exponent. Now we know the exponent needs to be 9, and we'll get back to how we need to calculate that exponent in just a moment when we have to store it. But let's look at what we have so far. We have figured out that the sign is 0 because the number is positive. So recall the formula we were using earlier. the negative 1 to the sine power times our mantissa times 2 to the e power? Well, let's take the information we have and plug it into that format. And for the sine, we'll plug in 0. So now our negative 1 in parentheses to the sine power becomes negative 1 to the 0 power. So once we plug in the 0, this is how our formula looks right now. When we converted 975.75 base 10 to our binary number, well, we're going to only use part of this number as the fraction. And I'll explain that in just a moment. But let's concentrate on the exponent. The exponent is a little different because we just can't plug in the number 9 into the bits representing the exponents. If we used a signed integer for the 8 bits representing the exponent, then negative exponents would actually look larger than positive exponents. For example, if the exponent is a negative 1, the signed 8-bit representation would be 1111, 1111. Whereas the exponent for a positive 1 would be 00000001. This can be misleading because we know a negative 1 is less than a positive 1. So how did they solve this? Well, they solved it by creating a bias. I think of it as a balancing point or a midpoint in the exponent where the exponent itself is recognized as a 0. Therefore, a signed exponent is not necessary. We don't have to worry about if that first digit is signed or not. It may seem a little confusing at first, but once you start getting used to using it, it isn't that bad, I promise. For example, the exponent in our problem is 9. And remember we said earlier that the bias is 127. And 127 represents 0 in our exponent. So if we add 9 to 127, we come up with 136, which is represented by the binary number 10001000. And now, if we plug in the 136 binary representation into the exponent bits, this is what we get. If we think about this backwards, sort of, we know that if the exponent's field value is 136, and of course that's base 10, and we subtract 127, which is our bias, we get 9. So we know the exponent we calculated when we normalize the binary representation of the 975.75 to the base 10, we know it was 9. Basically what we're doing is we're just going to add whatever our exponent is, we're going to add 127 to it, and that is going to be the exponent value we are going to store. That's if we're converting from base 10 to binary. We're going to know to add 127 to our exponent in order to arrive at the value we need to store in the exponent. Now let's recall the formula we started working with. So far we've got negative 1 to the 0 power times our mantissa times 2 to the e. Now we can plug in our exponent value into the e of this formula. Now some people like to write this formula as negative 1 to the sine times the mantissa times 2 to the exponent minus the bias. Because remember, when you're doing your formula here, you don't want to put your exponent in the e value because that's 136. You need to subtract the bias. By having the bias, it allows us to have a much larger range of numbers. If we follow this formula, we come up with negative 1 to the 0 power plus the mantissa times 2 to 136 minus 27, which in turn is negative 1 to the 0 power times the mantissa times 2 to the 9th power. Now our formula is almost done. You might be asking yourself, which part of that binary number we converted are we going to use? Before we answer that, let's take a quick look at this formula again. Remember the 1 plus f term in this formula is the mantissa. Notice how the mantissa adds the number 1 to your fraction. Why does it do that, you might ask? Well, I'll tell you. Remember when we normalized our binary number and the only digit to the left of the decimal point was a non-zero number? Well, for binary numbers, that only leaves a 1 that it can appear to the left of the decimal. The brilliant folks that came up with this format realized that by adding 1 back to the formula within the mantissa, they could add another bit to the fraction. So in other words, if the 1 is always implied because it is always there, why bother using a bit to represent it, and why not add that extra bit to the fraction? So you might ask, why would you want to add an extra bit to the fraction? It's just 1 bit. Well, remember, when we increase our exponent size, the range of a number that can be represented increases. When you increase the fraction size by adding that bit, then the precision of the number that can be represented is also increased. So using the extra bit in the fraction instead of using it for the 1 that is always present, it just makes sense because we're using floating point representation to make it more precise. So from the converted 9.7575 base 10 to our binary number, we are only going to use the numbers after the decimal place. 111, 00, 11, 11, 11. So when we fill in the fraction starting from the left to the right with this number, any bits left to the 0 position will be padded with zeros. Now that we have seen how the 32-bit representation is populated, let's take another look at the formula. So far it looks like this. -1 to the 0 times the mantissa times 2 to the 9th. But since we know our fraction, we can populate the f variable now. So what we'll do, remember how we build up a number, we will take 1 of our fraction is a 1. So we have 1 times 2 to the -1. Notice the -1 is the first position after the decimal, plus 1 times 2 to the -2, plus 1 times 2 to the -3, plus 0 times 2 to the -4, because that fourth position there in our fraction is a 0, plus 0 times 2 to the -5th, plus 1 times 2 to the -6, and it goes all the way out to 1 times 2 to the -11th. Now we could continue all the way to the 23rd, but all of those are zeros, so anything times 0 is going to be a 0. So we'll just stop it there for simplicity's sake. If we actually do these calculations for all of the 1s that are multiplied by a 2 to some power, we come up with all of these numbers here. I'm sure you can see them. I'm not going to read them all out number for number. But it ends up equaling 0.90576171875, which is the fraction that we will plug into the formula. Now keep in mind, if it is ever greater than 1, there's a problem with your calculations. You'll have to redo it, because since it's a fraction, it should never be over 1. So now we can see how our format is populated with a sign, an exponent, and a fraction. If you went ahead and wanted to check your work, you would have -1 in parentheses to the 0 power times your mantissa, and then you would multiply that times 2 to the 9th power. And that becomes 1 times 1.90576171875 times 512, which is 2 to the 9th, and that equals our number. Now you may say, oh my gosh, there's 0.0000352 additional to that. Since we're calculating by hand, we might come up with a tiny bit of a difference compared to if we were running this on a computer, where IEEE requires a guard digit to help make numbers more precise. And that is for another video maybe. There are many websites about this online if you want to investigate it further. Thank you for watching and have a great day.